Welcome to Calculus 1. In this video, we're going to talk about limits at the infinity. Alright, so just like when we talk about limits before, assuming L is a real number, as a limit of function of x approaching to infinity, if my limit is equal to L, that means for each epsilon that is greater than 0, there exists a number m greater than 0 such that the absolute value of my function minus the limit is less than epsilon whenever x is greater than n. Alright, same thing for the limit going to negative infinity, okay, of my function is equal to L. That means now for every epsilon that is bigger than 0, there exists a number capital letter n that is less than 0. So because we're going to the negative side, such that the absolute value of my function minus my limit will be less than epsilon whenever x is less than n. So my graph here is for the number 1, for the positive infinity. So as you can see, what happened is my function f of x, okay, as it keep on going to infinity, it will actually be within so many units. Okay, the epsilon will be within so many units of my L, okay, as x approaching infinity. So eventually my curve will actually taper off at L, okay, as the epsilon getting closer and closer to my L. Alright, so the whole purpose of showing you the graph like this is to tell you that a lot of times when limit of a function as x approaching to infinity, okay, my limit will converge to be one particular number. And that number, a lot of time, will actually become our horizontal asymptote. Okay, so the line y equal to L, will be the horizontal asymptote of the graph of my function f. Okay, as my limit of function approaching to negative infinity or positive infinity. All right. So a couple special cases here before we do more examples. Alright, so let's say R is a positive rational number and C is any real number. If I'm taking a limit of a constant or a number divided by x to some kind of power as x approaching to infinity, my limit will be 0. Same thing if I will actually approaching negative infinity, my limit will be 0. Okay, so for the negative infinity, this x to r power got to be defined when x is less than 0, got to be negative. Alright, another basic one is limit of e to the x as x approaching negative infinity. Okay, the limit will be 0. If I'm going to take a limit of e to the negative x power as x approaching to infinity, it will also equal to 0. And another way to write e to the negative x, as you know, is 1 over e to the x. Okay, so those limit will equal to 0. And the graphing, if we graph this function, you can kind of see by looking at the graph, you can tell as x going to the left or x going to the right, eventually the limit will approaching to 0. So other than graphing is a very, very powerful technique to find the limits, okay, at infinity. Besides graphing, if we use some of these basic rules, it can kind of help us real quick as well. Okay, so as we can recall, the limits of the difference, I can actually split this limit up as limit of 5 as x approaching infinity minus my limit of 2 over x squared as x approaching to infinity. So limit of 5, it was just going to be 5. Alright, limit of 2 over x squared, okay, a constant, let me go back down here, a constant over x or some kind of power, the limit will always equal to 0. So this is going to be 5 minus 0, which tell me that my limit is going to be 5. Alright, if you want to take a step further and graph it, you will actually see the horizontal asymptote, f5. Alright. So this one, I'm going to factor out the 5 out. So that's going to be, take a 5 times the limit of 1 over e to the x, okay, as x approaching to infinity. And earlier I said e to the negative x is the same thing as 1 over e to the x, and the limit for that we're going to be 0. And 0 times 5 tell me my limit is going to equal to 0. Now, when it comes to dealing with rational functions or complicated functions, okay, we can either go by graphing or go by this guideline. And this guideline is really for a simple rational functions, okay, where you can kind of look at it and tell. Now, for more complicated rational functions, I personally believe that graphing is one of the best ways. Now, a lot of times when we're dealing with limit at infinity, we get very, very creative on how on manipulating our rational function. So I'm going to show you that real quick, and then I will go by this guideline. Alright. You see, in many cases, with like example like this, in many cases, as limit approaching infinity, okay, we actually create what we call an indeterminate form. 2 times infinity plus 7 will actually tell me it's going to be infinity, because 2 times a very large number plus 7 more will still be infinity. 3 times x squared, 3 times infinity squared, real big number squared times 3 plus 2 will still be infinity. So this is called an indeterminate form. So when we run into indeterminate form, that means we need to start manipulating what our rational function will be. And this thing gets a little bit too creative sometimes. So for this particular example, what I want to do is multiply the top and the bottom by 1 over x squared over 1 over x squared. So what that will lead us is the limit as x approaching to infinity. Okay, 1 over x squared times 2x plus 7 will give me 2x plus 7 over x squared over, okay, this one in denominator, same thing, 3x squared plus 2 over x squared. Now if I look at the top, these two terms share the same denominator, so 2x over x squared, limit as x approaching to infinity, this is going to be 2 over x plus 7 over x squared over 3x squared over x squared, which is going to be 3 plus, split this up, this is going to be 2 over x squared. So the reason why I times by 1 over x squared over 1 over x squared is so that I can create something look like this. And that's the trick. How do you know go from the original rational function to make it look like this, so you can take the limits? So for a complicated function, it's really hard for us to really know exactly how to manipulate, because we don't really know what we need to look at the very end. So for this particular problem, what I really want to look at the very end is breaking up all my terms, where I can actually take a limit of each one. So limit of a 2 over x, that's gonna go to infinity. Okay, think about it like this: a number divided by something real big will actually close to well, excuse me, not infinity, I'm sorry. I did not mean to say infinity. I meant to say 0. A number divided by something real big is almost going to be 0. Okay, so I'm using this concept right here. All right, again, a number divided by something super large will actually gonna be 0. 3 stays as 3. A number divided by something real big is gonna be 0. So what I end up with on the top when I take a limit is 0 divided by 3, which is 0. Okay, so this is actually, so I figure my answer by manipulation, okay, of my rational function. The easy way is just go by the guideline. Okay, the guideline is actually talking about the degree of the polynomial for the top and the bottom. If the degree of the numerator is less than the degree of the denominator, the limit is 0. So if you look at this one, for the 2x, the degree is 1. For the 3x squared, degree is 2. Okay, so technically speaking, as x approaching to infinity, the bottom number is actually a lot bigger than the top, because I'm actually taking infinity squared. So that means when I take any number divided by something super large, eventually that's going to tell me my limit is going to be 0. Okay, you can put in the calculator, just take a small number divided by a super large number, will actually become 0. Alright, the next guideline is saying, the third guideline is saying, if the degree of the numerator is equal to the degree of the denominator, then, then the limit is the ratio. Sorry, this will be TG. Then the limit is the ratio of the leading coefficient. So without manipulating my function here, when the degree of the top and the bottom are the same, okay, and then the leading coefficient, okay, will be the limit. So that'll be 2/3. And that's a lot like finding the horizontal asymptote, okay, of a rational function. Alright, if the degree of the numerator is bigger than the degree of the denominator, in that case, it really depends on the function itself. Okay, here is simply saying, if a degree of the numerator is greater than the degree of the denominator, then the limit does not exist. And I do agree with that. Because that does not exist means you're going to end up with an infinity on top divided by something else at the bottom. Because the top infinity is bigger than the bottom infinity. So you will still end up with to be does not exist, which is infinity. But if I would do this problem by manipulation, okay, just like the one I did earlier, again times by 1 over x squared for the top and bottom, 2x to the third plus 7 divided by the x squared over the 3x squared plus 2 divided by the x squared. Okay, what they're gonna end up, okay, is gonna be 2x plus 7 over x squared. And the bottom is gonna be 3 plus 2 over x squared. So if when I take a limit as x approaching to infinity, this term will actually become infinity. This is going to approach into 0. This stays as 3. This one, the number divided by something super big, is going to be 0. So infinity plus 0 is still infinity. Divided by 3 plus 0 is 3. So a real large number divided by a constant is going to tell me it's infinity. Alright, that's manipulation. This is going by the guideline. Or if I can do it by graphing. I don't know if you remember learning about something called a slim asymptote. Slim asymptote only occur when the degree of a numerator is 1 bigger than the degree of a denominator. So to find a slim asymptote, we actually do long division. And let me show you, because this is something that you really don't see when you graph it. 3x squared. What I mean by you don't see is you don't see the slim asymptote. All right. So this is one part of the. Let me make sure I'm typing it right. 2x plus 7 plus 7. 3x squared plus 2. Yep. So there's a slant asymptote right here. There's a straight line actually keep these graphs not going below this this line right here. There's actually a straight line here, and my graph is actually above it. I think there's another part of this graph for some of these rational functions. So when we talk about limit going to infinity, what we are looking at is, as x keep on going to the right, what is my y value doing? And my y value apparently is actually keep on going up. Okay. I can go to my table and confirm that, or I can go to my value and confirm that. Okay. So graphing always help. Okay, always help to confirm. Now, if we run into a very complicated problem, like this rational function, x over x squared minus x, the manipulation we have to do for this problem, okay, is almost horrendous. So why not kind of graph it and see what we are looking at here? Minus x. I'm gonna close my parenthesis. Okay. So if I want to go to negative infinity this time, that means x is keep on going to the left. Okay. As x keep on going to the left, over time, tell you what, I'm gonna do it this way. I'm trying to see if I remember it. I already typing my function under y1. Alright, so let me see if I remember this. Go to vars, y-vars, and number one function, and extract this thing called y1. And this y1 is the same as what I just graphed. And open the parenthesis up and just typing any x value you want. So since my x is going to negative infinity, I'm going to go to like negative 10 first. And see, this is negative 0.95 something. Second entry, let's do negative 100. Oh, negative 0.99 something. So if I keep on going bigger, do 1,000 this time, negative 0.9995 something, you can start seeing the pattern as x going to go into negative infinity. I begin to converge onto a particular y value. So this time I'm going to do a lot of zero. And it's going to tell me it's negative 1. Okay. Alright. So we talk about one of the key reasons we talk about limit infinity here is the next set of materials. We're going to take a look at the area under the curve where we will actually need to take a limit as x going to infinity. Okay, that's one of the reasons why I want to introduce it here at the end of module number 4, or the section 4.5. All right, thank you for watching.